So our first speaker is Mehdi Moghaddamfar. He's a PhD student at the Technical University of Dresden. He's collaborating with SAP on a research project with the goal of leveraging FPGA technology for database system acceleration. The product of his research is a system on chip capable of processing the most frequently used pipeline breaking database operators on a wide range of workloads. Mehdi.
Thank you for the introduction. Hello, everyone. So without further ado, let me start the presentation. All right, so this is the agenda. I'm going to start by introducing aggregation and then early aggregation as a method to improve the performance of aggregation. I'll then pose the research question, which is, what's the best way to perform early aggregation on FPGAs? I'll then introduce some of the ways it's been done before, so the state of the art, and then compare those ways through our simulations. The goal, of course, is to come up with an architecture that's well optimized for FPGAs. I'll then present an implementation of that architecture and some benchmarks on that. I'll finally conclude the talk with a summary of our contributions. So a relational database is basically a bunch of tables, and a database system's job is to run operations on those tables. Now, one of these operations is called aggregation. And what's special about this particular operation is that it's both very commonly used across different workloads, and it's very computationally intensive. And that has made it into a target for FPGA-based acceleration. So here's an example of the aggregation operator. You start, of course, with a table with a key column K and a value column V. And then, so the idea of aggregation is you want to group the rows of the table that have some common attribute. So in this case, it basically said you want to aggregate it based on a key column K. So those rows that have the same key are then grouped together. And then you would sum the values of those rows. So that would give you 1 plus 2 plus 1, which is 4 on the right. And so you do that for all of the groups in the input table. Now, one of the ways aggregation is typically implemented uses sorting. So here you would sort the table, and on FPGAs, it's typically done through the sort merge algorithm, where you start by sorting parts of the table, producing sorted runs, and then you would merge those sorted runs into the final result. And then once that is done, all of the rows belonging to the same group, right? For example, here again, the group with key 8, they come one next to each other. So you can just go through the table and aggregate them on the fly very easily. Now, the inefficiency with this is that sorting is expensive. So you want to sort as few data as possible, right? Now, here comes the idea of early aggregation. So early aggregation is sort of a best effort algorithm that tries to aggregate as much of the data as possible earlier in the process before complete aggregation takes place. So, for example, the algorithm could look at rows that are neighbors that come one after each other. And if it finds neighbors that have the same, that belong to the same group, it would aggregate them right there on the fly. So here, the two rows with key 8 that are in the green box are aggregated together. But the one in the red box is not aggregated, and that's because it's not a neighbor of the ones in the green box. And that is okay, because later on, we still have full aggregation come and finish the job. So it does the sort and the merge and the aggregation later on. And so the advantage is, of course, that the size of this intermediate table is smaller, so there's less data to sort, so you get better performance. We also get, so because of this, the memory footprint of the algorithm is also reduced, which means that we can support now larger tables on FPGAs that have limited memories typically. And so, yeah, so that's kind of the idea of early aggregation. And of course, as I said, our research question is, what's the best way to do this on FPGAs? So what's the best way to do early aggregation? So let's talk about how it's been done before. There are two major categories of early aggregation algorithms. One is sort-based early aggregation. And so here's a general like here's like the architecture of how things go. You have the RAM of the FPGA that has the table on it, and you would read rows of the table one by one into the early aggregation algorithm, which has a buffer of fixed size. This is an unchipped buffer. And then whatever comes out the other side, and I will define that in a bit, then gets completely aggregated via, the traditional aggregation algorithms. So the way sort-based aggregation works is you would read a row from the RAM, right? You would compare it to all of the rows that you already have inside the buffer. If you find a matching row, you would then aggregate them in the buffer. If you don't find a matching row, you would just add this new row into the buffer. And if at some point the buffer is full, you would sort whatever's in the buffer and output it as a sorted run. Right? And then that gets completely aggregated later on. Now, because of the complexity of this algorithm, the way it's typically implemented is via multiple modules that work in parallel. So you would distribute the rows to these modules, right? They would do the early aggregation, and then you would collect the sorted runs coming out the other side. This, of course, also means that the buffer of the early aggregation algorithm has to be split between these different modules. Now, the second category of early aggregation algorithm is based on caching. So here you have the exact same structure, except that the buffer is laid out as a cache. And so here's an example of how it will work. You would get a row with a key 1, for example, here. You would then hash the key of that row, and that would give you an index into one of the sets in the cache, right? So in this case, it's the last set. If you find a matching row, so another row with the same key, then you would aggregate them. If not, you would insert this new row into that cache, so into that set, potentially evicting some things that's already in the set, how caches work, right? So these are the two ways that it's been done before. Now the question is which one's best? And so we've done simulations to compare these techniques. Now, these are the metrics we use in our simulations, which I'll illustrate through this example. On the left, you have table R, which is the input to the early aggregation algorithm. Now, the early aggregation algorithm has a buffer of size 8, so it can hold 8 rows or groups at a time. On the right, you have the result. So here are the metrics. We have memory factor, and that is the number of unique rows or the number of groups in the input table, which I have here color coded. So there are 4 of them, divided by the buffer size of the early aggregation algorithm. And so the smaller this number is, it means that basically the early aggregation algorithm has a better capacity to hold the table inside, to absorb more and more rows. Then I have reduction factor, and that is basically the performance of the early aggregation algorithm. So that's how many rows you get at the output. So the number of rows in table S divided by how many rows you get at the input, right? And so the smaller that number is, the higher quality early aggregation algorithm you have. Here are the results of our simulations. We used a data set with the zip distribution, an exponent of 1. On the y-axis, you see reduction factor. The lower, the better. The blue bars represent cache-based early aggregation, and the brown bars represent sort-based early aggregation. And what you can see here is that cache-based early aggregation seems to perform much better across all of our different memory factors. And there are two main reasons behind this. One of them is that, as I said, for sort-based early aggregation, this buffer size, this buffer of the early aggregation algorithm has to be split between the different modules. And so it gives that a lower effective buffering capacity. And now the second reason is that for sort-based early aggregation, once the buffer becomes full, once the buffer of the early aggregation module becomes full, it then sorts it and flushes the entire buffer. And that is too drastic of an action, basically. Because if you compare it to caching, once the cache is full or a set of the cache is full, then you would, when a new row comes in, you would evict only one of the elements in the set, whereas for sort-based aggregation, you would evict the whole buffer. Okay, so cache-based aggregation seems to be the way to go. Now here's another set of simulations comparing this time different degrees of associativity for cache-based aggregation. And going from left to right, from the blue bar to the purple bar, we basically exponentially increase this degree of associativity. We go from 2 to 4 to 8. And what we see is somewhat of a logarithmic decrease in the reduction factor, right? So we have diminishing returns. Now, the other thing that should be considered here as well is the degree of complexity of the algorithm. So as the degree of associativity of the cache increases, you need wider block RAM memories, you need more comparators, and you need more complex logic to run your replacement policy if you have one. And so throughout our simulations and our benchmarks, we saw that 8-way set-associative caches present a good balance between implementation complexity and the aggregation performance. So reduction factor here. All right, so then the next question is, how would you implement these, right? Now, the basic way, I guess, of implementing a cache for this particular domain is the following pipeline. So you would get a row, you would then compute the hash of its key, you would then fetch the corresponding set from the cache. You would then, according to the algorithm that I explained earlier, see how you would update that set. And then finally, you would actually update the set. Now, there are two challenges due to two hazards that this pipeline has to deal with. And we have hazards due to key collisions. And that is if you have two rows that have the same key that come after each other, right? Well, one of them has to be stalled until the other one goes through the pipeline before this one can continue, right? And we also have hazards due to hash collisions, and that is if you have two rows that have different keys, but that have the same hash, right? And that's an actual hash collision, right? And so in that case, again, one of them has to be stalled till the other one updates the corresponding set. Now there are some solutions to this problem. The one we propose is application specific, and so here's the idea. Let's say this cache has a pipeline of depth W. So it takes W clock cycle to go through the cache and update the targeted set. Now, if I make sure that within my stream of rows, so I have a stream of incoming rows, within every window of W rows, there are no key or hash collisions, then the cache does not need to deal with these types of hazards. So so here's what we propose. On the top, you can see that so this is our pipeline going from top to bottom. I have a cache that has a pipeline of depth 3 in this case. So W is 3, right? And so here's a stream of rows that I'm showing as an example from left to right. Every tuple is a row. So here A is the key and 1 is the value attached to the key. A window aggregator basically looks at every window of 3 rows, so W rows, and if it sees 2 rows that have the same key, it would just aggregate them on the fly. And so I've color coded this for you. After this step, you'll get to this, right? Now, underscores basically mean that there's been a row here before, but it's already been aggregated, right? So for example, the red ones, you have A1 and A1, and that's been aggregated into A2. And so we don't need to consider A1 anymore. The compressor then eliminates these empty rows or these underscores. The hasher would then add the hash of the keys to the rows. So for example, the hash of A here is, let's say, X, right? The collision detector is maybe the more interesting module. It it augments the rows with what we call release indices. And so the release index of a row is the index of that row within a new stream of rows. So basically, well, actually, let me explain the next module as well. The collision resolver then enforces these release indices. So let me show you an example. Here, the first row, A2, has a release index of 0, right? So it becomes, so in the new stream of rows, which is shown below, it comes at index 0. The next row in green, B3, has a release index of 3, and so it becomes at the third index of this new stream of rows. And so if you look at this final stream of flows, you'll see that there are no more key or hash collisions within every window of 3 rows. And so the cache doesn't need to deal with those anymore. All right, so how do we implement this? Well, the window aggregator, it's actually composed of a bunch of distance aggregators. So a W distance aggregator basically aggregates 2 rows that are exactly W rows apart, right? And so the design is quite simple. You have the shift register. It shifts in W rows, compares the first one and the last one. And if they're the same, it just aggregates them. The compressor is quite trivial, right? It just eliminates empty rows. The hasher, well, it's not really the focus of this particular work here. The collision detector is the next interesting module. This is the module that creates these release indices. Now, the way it works is it shifts in a window of W rows, right? And then it compares the hash of the last row with the hashes of all the other rows within the window. And what it does is it finds the closest row to this last row that has the same hash, right? Now, if there is no such row, right, then the release index of this last row becomes the release index of the row that came before it plus 1, because there's no collision. If there is a colliding row, then the release index of the last row becomes the release index of the colliding row plus W. And this makes sure that they are W rows apart. And so they won't be in the same window anymore. Now the collision resolver, the next module, that one's also quite trivial. It just enforces the release indices. And then we get to the cache, which, thanks to all of these pre-processing stages that I just explained, is also quite simple to implement. You just have the cache memory, you index into it using the hash of the key, and then you perform your updates and finally update the cache memory. So the design is now quite simple thanks to these pre-processing stages. All right, so let's talk about our benchmarks. We use a platform named MSM for our benchmarks. This is a state-of-the-art database system accelerator. So to perform the aggregation operator, it basically uses the algorithm that I explained before. It has 2 pipelines, a sort pipeline in yellow and a merge pipeline in blue. The sort pipeline basically sorts the table, like creates sorted runs, and the merge pipeline merges those sorted runs and then aggregates them. So you see the aggregates in the merge pipeline. Now, the way we modified this, and we call the new platform cache-based MSM or CBMSM, is instead of this sort pipeline that previously used sort-based early aggregation, which I explained earlier, we now use cache-based early aggregation, this new architecture that I just introduced. And that's basically it, right? We still need some sorters because the aggregation algorithm still needs to perform sort, merge, and then aggregate. But now we use cache-based early aggregation. So these are the results of our benchmarks. We have MSM on the top, CBMSM on the bottom. Now we have here sort times and merge times. So on the y-axis, we have execution time. Now the sort time of both algorithms, and so that's the time it takes to go through this sort pipeline, is actually pretty much the same. And the reason for that is that both of these pipelines have been designed to process 1 row per clock cycle. So they can really run at full throughput. So they run the same amount of time. However, the merge times in dark blue are much smaller for CBMSM. And the reason behind that is that there is less data to merge. And that's because cache-based early aggregation does a better job in this case, right? Compared to sort-based aggregation. And that's what we saw basically through our reduction factors. And so looking at end-to-end aggregation performance, we basically see that CBMSM runs around 2 times faster compared to MSM. So let me conclude with a brief summary. I've shown you a small comparative study of the aggregation of different aggregation algorithms, sort-based and cache-based. We saw that set-associative caches achieve a pretty good balance between like implementation complexity and the aggregation performance. I've then introduced a novel architecture, an application-specific architecture for implementing these set-associative caches. And finally, we saw that a platform using this new early aggregation algorithm runs 2 times faster than what it could do before with sort-based early aggregation. Now, a few other things that are in the paper that I didn't have time to go through are simulations on much more sophisticated early aggregation algorithms than the ones that I introduced here. We also have simulations and benchmarks on a lot more data sets. And I also present a much broader discussion of implementation complexity of these different early aggregation algorithms. So thank you for listening, and I'm open to any questions.
Very nice, Chuck. Thank you. I have a more system level question. So typically when you have databases, specifically if you have row-oriented database, there are operations like projection and selection that you need to do before you come to an operation of aggregation. And so when you talk about early aggregation, are you talking about those operations even before selection and projection is happening? And if not, after that, you have to store that intermediate result somewhere, and then you have to take multiple passes through, because you probably require 1 pass for the early aggregation and then the second pass for the main aggregation. Have you considered the overall end-to-end performance implication of your schemes on that?
That's a really good point. So actually, early aggregation is supposed to be extremely lightweight. So it's supposed to be, so we're supposed to be able to run it just before aggregation. And that's what you can see in our in our architecture here. So just before aggregation happens, data goes through this early aggregation module. And the early aggregation module does not need to access RAM or anything like that. It's basically a bump in the wire, you know? So it's just like a new stage in the pipeline. And so yeah, basically it just happens before aggregation after all of those projection and filtering stages.
Yeah, you did not compare your performance relative to a CPU or a GPU. And I mean, you basically compared what was before and what is now, both on FPGAs. So how does that compare to a CPU, for example?
That's another very good point. So I do that in the paper. And so the thing is, so let me look at, for example, the uniform data set here. The smallest bar you can see here is the new platform. The brown one is the old platform, and the green one is the CPU. So we've already been quite faster than the CPU before, around 5 times faster on average across all of our data sets. Now with this new platform, we're around 10 times, 15 times faster than state-of-the-art in CPU.
We're going to move on to thank our speaker once more.